Our speaker this evening has previously worked at Bell Research Labs, Intel, and Microsoft, holds several patents in computer architecture and distributed computing, has a PhD in parallel computing, and had a previous company acquired by Microsoft. Please welcome the CEO and founder of ScaleOut Software. Thank
you very much. I've never been applauded before and talk. I want to hold that. So, okay, we're ready to go here. I have my...
I can't hear you in the back.
All right, so this is the agenda for tonight. Can you hear me in the back? Okay. You can?
Well, I can just hear you.
Okay. I can't get any louder without a mic, so I have a little bit of a cold. So I'll talk as loud as I can, but just raise your hand if you can't hear me. Okay, and I'll try to talk right at you. Okay. So we're going to talk about operational intelligence, which is a term that's been around a long time. We're co-opting that term to talk about delivering real-time feedback to production systems. So for example, an airline reservation system, and there are problems with weather, and you want to reroute passengers immediately, that's operational intelligence that allows you to do that. But you'll find other uses of that term going back decades. We're going to talk about how we can do this with data parallel computation and in-memory computing. I'm going to start with an example of cable viewers. We did a proof of concept for a cable company last fall, and it's a really good example of how operational intelligence can allow a company to have a competitive edge that it otherwise might lack. And I have a little video which, if the audio works, I'll play for you in a minute. And then we're going to talk about how we implement data parallel computation using our in-memory data grid. This is not product-oriented, although there are features in our product line which I have to talk about because that's what we've been working on. But I don't want you to confuse this with a vendor pitch. I'll do my very best to avoid that. And then I'll give you some more examples. In particular, we'll look at an example in financial services with a hedge fund we work with here in New York and talk about how this method of data parallel computation, object-oriented data parallel computation, can be used to solve this problem and give real-time feedback to a hedge fund. So, okay, I think we can go to the next slide. So just there is one vendor slide. ScaleOut Software has been around since 2004, and we first shipped our in-memory data grid product in 2005. I came out of Microsoft, and when I left Microsoft in 2003, there was no solution to the problem of you have a web farm with a whole set of web servers. Where do you share session state? This was a genesis for the company. Sometimes people are interested in how does a company get started? Why did you care about the technology area? And I've always worked in parallel computing, both before and after Microsoft, but I saw this problem, which is that people were pushing all the data for the web servers into, where do you think they put that data? Database. And a database is not the right repository for fast-changing business logic state. And so the idea of putting that in memory, bringing it closer to where the web servers are using it, would reduce access latency and provide scalable throughput and scalable storage capacity. And so we started this company to do that. And in fact, we, to go a little farther than that, since this is an evening talk, I'll just say some things I wouldn't normally say during the day. We realized that people wanted to use the APIs almost immediately. I thought the lifetime of this company, we would never, customers would never use our APIs and just plug into Microsoft's environment initially because they had a provider model that was missing from Java Linux at the time. And so we immediately rolled out APIs, and then we found that people wanted to do parallel computation with this in-memory platform because of the fact that you could store data and in memory and have it automatically distributed across a cluster of servers. The fact that the grid is doing that for you automatically creates what we used to call at Intel supercomputers a domain decomposition for data parallel computing. So the application developer doesn't have to do any work. And the net result is that you can very easily write data parallel programs and get very fast computation times with in-memory computing. And so we'll talk more about that, but that's the evolution of our company. You can go ahead. Okay, so we're the audio was flaky. It worked, it stopped, it started again. If it works, then it's a 2-minute video. And do we know where the volume control is? In case you have it, okay. Go ahead, here we go. You know, Murphy's Law, the audio won't work. So, and in fact, it doesn't work. Why don't you just let it play for a minute? And so this is a video we did last year. It's too bad it's got a compelling audio track to it. And I don't know why in Windows with HDMI it sometimes works and sometimes doesn't. But the point is, it's showing you how you're going to a website and you know, a customer is just going to pick out a barbecue, but the website knows all about that customer, but is not leveraging that, and so they're allowing the customer to buy a low-end, unsatisfactory barbecue. But if you use in-memory computing, then you get beyond this problem of having the wrong barbecue to having being upsold the barbecue that really meets your needs. I'm sorry, I'm blocking your view. So that's what operational intelligence is. I've never tried to voice over manually, but this is explaining how using in-memory computing, you can very quickly ingest events, which are coming up, I think, in just another frame here. And then here come the events, watching the click stream, and figure out, personalize the offers and send them back out to customers on an e-commerce website, and thereby you have the benefit of much more personalized and effective marketing of your products to customers. Now what we've done is, and you can pull profile information out of the database that you've collected, and you know, we've talked now to several companies about doing this, and this is starting to really take off. I think in another 2 years it'll be commoditized, if you will. Everybody, the large e-commerce retailers will be doing this. And it applies to many vertical markets, and there's the last scene. He's happy now, there comes his wife, and they're all happy with their big barbecue. So that's the end of that. Okay. That was 6 months of work.
So in other words, how you use memory technology, you get a faster scale out and a faster processing queues.
Yes. What he's saying is faster. Yes. What you can get low latency, maybe within milliseconds to a second, you can get responses. Now, I was at a organization today in Long Island that's doing real-time patient monitoring. You could use this exact same technology to do real-time patient monitoring. And imagine the value of that on a hospital floor when you have telemetry. And this guy who's an expert in this was explaining to me that, on the hospital floor, they have all these machines spitting out telemetry, and guess where it's going? It's going into a database for the EMR system. And there's no software that's looking at that telemetry and trying to decide, would this patient need a nurse right now because something bad is about to happen? And the big part of the problem is that when a doctor comes in, they look at the telemetry at that instant. They look at maybe what the machines are saying and look at the chart, but they don't go back and look over several hours to look at the pattern, the trends that have been occurring. So with this kind of technology, the computer can be watching the patterns and trends evolve during the course of the day. So that's like the 10th generation Fitbit will do this for you, if you have a medical condition, watching you and giving you a text message when something's going wrong. I think we can go to the next slide. So these are some examples of technology areas that can benefit from operational intelligence. We started out looking on Wall Street. This hedge fund example I'll give you was a good proof of concept that we did. We also looked at cable media, e-commerce. Internet of Things is another one. I just gave you an example of Internet of Things. Also manufacturing and logistics. We work with a company in Southern California that's matching perishable good orders for flowers with inventory. And because the inventory is very perishable and the orders may come in and, like Mother's Day, they get a whole bunch of orders, then they need to be able to match that very effectively without error, or they'll lose money instead of make money. And the problem was they were not using in-memory computing techniques to do this, and they had this data siloed in 2 different systems. And by using in-memory computing, they could now, within a few seconds, make sure when they accept an order, they can actually fulfill it. That's just another example. So these are, another case would be wire fraud, wire transfer fraud. And I'm talking to a gentleman in a bank who was explaining how they only have a few seconds to decide whether to allow a wire transfer to go through. And so with this technology, you can very quickly make a more intelligent assessment. Let's go to the next slide. So this is the cable viewer example that we're looking at. So we're talking to a cable company about a year ago they have 10 million set-top boxes in the Atlanta area. And their problem is that they're competing with all the, what they call over-the-top players, the Netflix and Hulu. And now you've seen HBO and CBS, everybody over the top, over the internet. So the cable TV companies really need a more competitive edge. And the way they want to achieve it is through cross-selling and upselling programming and making other offers associated with the programming. And in addition to that, they want to be able to identify when customers are unhappy because of a problem with their set-top box and just get it fixed even before the customer recognizes an impending failure.
How do you make money on that?
How do we make money? We license the software to run the operational intelligence that will deliver that value.
So how would you charge to the cable company?
How would we charge?
Yeah.
Well, we license our platform to run their application software.
So it's one of your paying customers?
Not today. We did a proof of concept. They're not a paying customer, this particular time. So, good question. Which are paying customers? Okay, so,
We'll make sure they are.
yeah.
After the presentation.
Thank you. Okay. So, so about 10 million set-top boxes. They get about 2.2 billion events per day, which is about 25,000 per second. And you can't imagine how long it would take them to correlate this data. The problem they have is these are channel change events, and they need to correlate them by set-top box, and they're not correlated when they come in over the network. Number one problem. Number two, they have to cleanse them. And there are two main cases that they explain to us. One is the person that's channel switching, you don't care, and the other is the person that falls asleep at the TV and watches its same show for 4 hours. You don't care because they're not really paying attention. So they need to they have all these cleansing algorithms, and then they need to enrich it with what are the programs they're watching, and then they need to feed that to, it turns out they have a recommendation engine, but you could imagine that this technology could implement a recommendation engine. So that, and then feed that back to the customer. Well, it was taking them 6 hours to do this correlation and cleansing and enrichment because of the fact, again, they were using disk-based solutions and putting in a database, and the correlation itself was taking a long time. So we had a competitor that said they could do the correlation and cleansing in 12 minutes, and I thought, I think we could do it in a few seconds. So we proved it to them. Go to the next slide. We built them this little console. We ran this on Amazon on 12 servers, and we demonstrated that we could do 30,000 with just 12 servers. We could cut that down to many fewer servers, but 12 was the number we chose just to make sure it performed very, very well. And so the two things that they wanted to be able to do was, first of all, do all this correlation, cleansing, and enrichment, but also they wanted to be able to look at aggregate statistics. So for example, what are the top 10 programs by zip code? And now that is in fact a MapReduce problem, right? You got group by zip code and then analyze all the set-top boxes in that zip code. That's a map problem followed by a reduce problem. So we demonstrated that in the bottom right here, and we chose San Diego as the viewing area and supplied actually live programming information, and did this with a simulated workload. Most of these proofs of concept use a simulated workload because it takes a real company a long time to generate their target workload. They're not at that level, but we can simulate that and really stress the in-memory computing environment to demonstrate the power to generate results. And we found out two big things. One is that we can do the aggregate statistics in under 10 seconds. We've since optimized that down. It started at 20, down to 10, now it's down to 5. And then the other thing is we found that we could do the enrichment and correlation in under a second. In fact, it can be done in the order of milliseconds using data parallel computing. So that's a really big jump from 12 minutes and then from 6 hours. So that shows you the value. Now by doing that, you can give offers in real time. Somebody changes to a channel. You could look at their history, decide what might be an appropriate offer, and serve it up before they can move on to do something else.
How would you do it at scale?
Well, this does scale, and I'll go into that in a little bit. Defer. Okay, please, next slide. Okay, so we're talking about operational intelligence, and that is, sort of a complementary to business intelligence, and that's why we chose this term, because this is very complementary. First of all, I'm sure, how many people have read about or used Hadoop or bored now by Hadoop? Okay.
What's that?
How many people think Hadoop is passé? It's not. The
It's
design
dead.
pattern is not passé.
It's dead.
Okay, dead, even worse than passé. But it's the design pattern of MapReduce, I think, will be with us indefinitely. It's the
But not in the form of Hadoop, that's for sure.
Well, yes, it might be in the next generation in the form of Spark. But in any case,
Not even Spark.
okay. All right, so let me move on. We're talking about with batch processing of static data sets, petabytes of data overnight. So a company like Safeway might use Hadoop MapReduce to look at their millions of customers in order to figure out what offers to generate, when you're at the checkout and they give you the little coupons. That's something you would do with Hadoop MapReduce. Now, what we just saw are some examples of what you do with operational intelligence. It turns out in every example we've looked at, the data set sizes are in the tens to hundreds of gigabytes. They're not in the multiple terabytes. The first question we always get is, well, how do you know the problem set will fit in memory? And the reality is, for real-time problems, the problem sets typically do fit in memory. So for example, that patient monitoring problem, you might want to monitor 300 million patients, but the amount of data per patient for the real-time monitoring is just a few kilobytes. So, you know, it's not going to be that much data. That's just one example. We saw the set-top box example. That turns out to be really small, under 100 gigabytes of data. So you're talking about, what's key is that you're talking about live data versus static data. Data that is churning and changing all the time. And that's why in-memory data storage is so valuable, because the data is churning. You don't have time to push it to disk and read it back in. And HDFS, which is used by Hadoop, is really not appropriate because it's an append-only file system. It's even worse for real-time because of the fact it's append-only. You can't update it. So in-memory computing provides a very nice complement. Now let's go on. And well, it's something we learned. We were talking to a large restaurant company last year that has many, many on-site restaurants. You know the name. They do pizza. I won't tell you who. And they also have e-commerce presence. And they were really looking carefully at installing Hadoop as their data warehouse, getting rid of their old generation stuff and rolling in Hadoop from one of the big vendors. And they also had this problem of all this real-time data coming from their restaurants. They actually know, you know, who's the manager, who are the servers, you know, how efficient are the servers at any given instant in time. They can give feedback back to individuals in the restaurant in order to optimize operations. And they can tell when they're running low on particular supplies and to start shipping supplies out to a restaurant, that sort of thing. So, and they have another problem, is that they want to be able to ETL all that data into their data warehouse for Hadoop, so they can look at it strategically. So it turns out that you can take these two technologies and plug them together. You can use in-memory computing in order to provide tactical feedback in real time, and also to ETL data, extract, transform, and load it into HDFS directly. They were storing it in a file system and using shell scripts to get it into their database. And with Hadoop, they were just lost. They had no idea how they were going to get it from HDFS. Well, in-memory computing, and I'll show you how we integrate with a Hadoop environment. That's a way you can solve that problem. Okay, next slide. So the two big challenges that we're trying to solve with in-memory computing are handling this large stream of updates and then providing real-time feedback. You can ignore the graphs; they're just eye-candy. So it's you know, those are the two big challenges that you have for operational intelligence. And let's go to the next slide, and we'll talk about how we address them. The key way to address this is with data parallel computing. Now, I've looked at parallel computing. I hate to tell you how long, but I will. I started an Intel supercomputer group in 1986. I realized when I say that to my development team, they just go, okay. So don't ask him anything because he's too old to know anything. So, but the fact of the matter is, people were struggling at that time to figure out how do you implement parallel computing for the newly emerging parallel computers. And you know, Intel and IBM were in a big war and trying to take over from Cray. You know, it's just another generation of battles between companies. And then, so we hired people like Cleve Moeller, the guy who created MATLAB, to come in and help teach us how. He was a guy who coined the term embarrassingly parallel. When he looked at the Intel Hypercube, and he found out if a problem had any communication, it would just grind to a halt. But if you made it so there was no communication between the nodes of the computer, it would go very fast. And that's why he thought of embarrassingly parallel, because he didn't have to do any work to get performance. But you know, two forms of parallel computing emerged as the two basic techniques: data parallel and task parallel. And you know, task parallel is something you see with the pipelines you can build with Storm. And data parallel is a technique we have deployed with in-memory data grids because it's a very natural platform to run data parallel programs. And the two reasons why I find it appealing and why we push it on our customers, and one, it's very simple. You write one piece of code and run it on a large data set. And the second reason is it's very fast, and it's fast because it avoids data motion. And in our studies, it's data motion that's killing performance, because anytime you move data on and off disk or across the network, performance just tanks. And I'll show you a graph of that in a little bit. And in fact, that was the genesis of Spark, right? Is that, you know, data is going into memory, let's leave it there and just keep doing parallel operators on it. And that was the big insight that led to Spark, amongst other things. So data parallel computing is a very simple and a very fast technique. Let's go to the next slide. And you can use it to implement operational intelligence. Go ahead and click once. This is a key insight that we've had in the last year. I told you we did all these proofs of concept. Some things bubble up as common between all of them. And the key thing that bubbles up And something that I don't see being pushed by either open source or other vendors is this notion of tracking a live system with an in-memory model. Now, I'm going to tell you more about how an in-memory data grid creates an object-oriented representation of whatever state you're trying to track. And because it's at the business logic level, that it integrates with, as we heard earlier, Java, C#, C++, object-oriented languages. It turns out, because you can do that, you can create collections of objects of a class, and those can represent real-world entities. So in the case of, look at some examples here, shopping carts on a website or financial portfolios. We'll look at 2 or 3 examples later, or set-top boxes. You can represent their state in memory and use the events to update their state. That's a different way of looking at this problem than Storm would look at it, right? Storm would say, let's look at the event stream and pick out something that looks interesting. But in fact, in many cases of operational intelligence, you want to have very rich context. And you can build rich context by keeping an object-oriented in-memory representation that the events enrich it, and you can pull data, go ahead and click again, you can pull data from a NoSQL store that will enrich it. So if these are customers at shopping at Nordstrom, you can pull their shopping history, their brand preferences, the sizes they like, what did they buy in the last 3 weeks. And you can enrich the real-time information coming in from the website and click again. You can then analyze that in parallel and click again and make recommendations. So that's what you could do with the use of an in-memory data grid. Now I'm pointing this out because I'll reinforce that when I talk about Spark a little bit later. This is something that actually is relatively hard to do with Spark, and it's extremely easy to do with an in-memory data grid. And by the way, our company is not by any means the only in-memory data grid vendor. There are several. But it's this ability to have an object-oriented view of data that you can have individually addressable objects that makes this a very easy way to represent a real-time live system. Go ahead, let's go to the next slide. So with set-top boxes, then the objects here would be set-top box objects as an example. And you have the ability then to analyze, first of all, when updates, channel changes come in, you can correlate that data very easily. We solve the correlation problem by simply updating the objects. Instead of having the event streams go to a database, pull them out, and then correlate them, you just let the events go into little collections within each of those objects, 1 object per set-top box. And then you can use data parallel computation on that to do the enrichment and feed that to the recommendation engine, as well as to look at aggregate statistics across all of them. So this is just one example. That's how we implemented it. Next slide. So this is Storm. I guess everybody knows about Storm. And it's so back when I was at Intel, back in those days, the problem that I had is we would write task parallel programs to run on a multi-node system, what Chuck Seitz at Caltech used to call a multi-computer. And the problem is it's very hard to tune performance, and it's very hard to establish correctness because you can create deadlocks very easily. I think it's probably hard to create deadlocks in Storm because it probably won't let you create circularities in the graph. I don't know that to be true, but I presume that they've addressed that. But there's a lot of data motion with Storm, and there is, which can harm performance. Plus, you as an application developer have to figure out how you organize the task graph. So for some applications where you're focused strictly on the events, it's really good. However, if you're trying to maintain a real-time model of a live system, this may not be the right architecture to do that the most easily, in the easiest possible way. So I'm not criticizing Storm in general. I'm just saying that data parallel versus task parallel. Data parallel, in my experience, is a lot simpler. And for problems where you're trying to maintain state and enrich that state, it may be a better fit than an event processing system. And, you would compare that to CEP systems that have been around for decades and other event processing and streaming systems. Okay, let's go to the next slide. So this is where we first figured out about the problem with data motion. And this graph was generated by a company on Wall Street called Lab49. Anybody heard of Lab49? Yes. Okay, good. So we asked Lab49 to write a data parallel computation in memory that would do back testing of their trading strategies, and they're experts on stock trading. We're not. So they implemented this very complex 8 algorithm back testing test, and then they loaded the grid with stock histories for thousands of equities. And then they ran it 2 ways. They first ran it using data parallel computation using the infrastructure we provide, where the data on one given grid server was analyzed only on that grid server. And then they used the other technique that was very popular, using a third-party product I won't mention, that was just a cluster scheduler. So they would, the cluster scheduler would hand out tasks saying, you do IBM, you do AT&T, and it would then just read the data from the grid. So we call that random access here. And you can see the problem is you start moving objects across the network, and you're starting to kill scalability. So got the question earlier about scalability. You get scalability by adding servers as you increase the workload. That's called scalable speed up. And I'm not talking about that tonight, but I assume all you guys know this, or guys and gals, sorry, what scalable speed up is and how that's different from Amdahl's speed up. And this was actually first identified by Cleve Moeller when he was doing LinPack, trying to make that run in a parallel computer. What he recognized is you can't make one problem, a fixed problem size scale by adding servers. But if you increase the size of the matrix, in his case, as you add servers, then you can get scalable speed up because you're amortizing the communication overhead across a lot more computation. And so that has proven to be true in pretty much every example that I've looked at. And a guy named John Gustafson, if you haven't read his paper, he actually gets the credit for it in the ACM. And so I recommend you read Gustafson's paper. Moeller and Gustafson both have papers on it, but you'll probably hear it as Gustafson's law. And so in any case, that's the beauty of scalable speed up when you don't have overheads that kill you. And so that's what you want to achieve. And by minimizing data motion, you can get to much better scalability. Let's go to the next one. This is the after dinner set of slides I have, just 2 or 3. So, and then I'm going to surprise Derek. Where'd Derek go? Anyway, with a one more trivia question. I kept one back. So okay. The point of this is to show you that data parallel computing has been around for decades, as have I, and I worked on that one too. And there's a lot of stories about that. And there's IBM SP1, but it started out with SIMD, so data parallel and hardware. So that, has anybody heard of thinking machines and the connection machine?
Yeah.
Okay. So who knows who was the founder of that company?
Danny Hillis.
Right. Okay. Now the trivia question is, what famous physicist worked on the connection machine? You said it first. It's for you. All right. All right. So Richard Feynman. That's right.
Did you work with?
What's that?
Did you work with?
Oh no.
You were at IPS. You were
I was at Intel. And you know, it's a battle. This is single program multiple data. So we were using commodity processors and special purpose networks. So we were
That's
building.
Cosmic Cube. That's Cosmic Cube.
Yeah, the original one. That's the second generation. And then we went on to building mesh networks. And that, all of this cut-through routing and all was developed for this class of machine. But at the time, the thinking machines people were doing it all in hardware, not trying to use commodity processors. And the problem Intel ran into with this, what caused them to kill the division, was that they'd spent all this money on a fast interconnect. By today's standards, you'd laugh, but at the time, 200 megabits was really fast back then. So in any case, gigabit, that's really fast. So, but in any case, the problem was that it takes so long it took 3 years to build a new generation, and by then Intel, with Moore's law, that is Intel after all, had a new processor that would obsolete the old version. So this had like 386, and then they would have the 586 in before they could build a new supercomputer, and nobody would care anymore. So one day you wouldn't be able to go near the machine because it was so valuable, and the next day they were pushing it to your office because they didn't know how to get rid of it. So it was pretty funny watching how fast technology changed processor speed in those days.
So what kind of CPU was it using? The 386 GX?
I think the IPSC2 was 386. The first was a 286. That was the 386.
In the Hillis sort of definition about data parallel computing, typically one of the things that's addressed is the ratio of the data to the N of CPUs. Of course, the silicon scaling laws were very different at the time, and commodity was not the way to go. And I'm very curious, when you invoke the mantra data parallel computing, that sort of makes me think of an extraordinarily simple processor, but very many of them. And one of the things I'm seeing is that if you're quoting, for instance, 12 servers, there's a ratio issue typically in data parallel, right? So at some level, it's control level or task level, really, truly down inside, but it's not, this synchronous style, more like the CM1 and 2. This is a tree
I mean, this is very fine grained, and this is very coarse grained by
yes,
in
right.
comparison.
But you're not really commenting on the notion of ratio of data to processor, and it really doesn't enter into your analysis.
No, it does, but
data parallel.
you're right. I'm not commenting, but there's many things we can talk about. But yeah, you just have to manage the overheads. So for example, the scheduling overhead, the networking, the communications overhead of the application, you have to measure for scalable speed up no matter what you're doing. There was a very good talk I just saw at the C++ conference last year and talking about atomic operators, and the guy said, you know, if you're not measuring, it just doesn't matter. You got to measure everything. And I realized, you know, we spend most of our time measuring scalability to find where the overheads are, the non-scalable portions of the code, and eliminate the overhead so that we can get good linear scaling.
But one of the emphasis that you trade on is the notion of shared nothing. That's a great
It
deal
is
of
shared
emphasis
nothing, yes, because
on this.
you avoid overheads with shared nothing that you would get with the Hadoop architecture. But again, we could talk for hours. Let's go to the next slide. And so then we see, you know, clusters became popular, and then cloud, right? So, but it's the same. Data parallel computing works in all of these environments, and you know, we used to talk about using message passing. Now we talk about MapReduce or son of MapReduce, whatever the next thing is going to be. We heard about, but in any case, I just wanted to give you a perspective. This stuff's been around for decades. Okay, go ahead. So this is the architecture. We've looked at it before. I'll just recap. Let's see where we are in time. Okay, and we've got about another 20 minutes worth of material. That's okay for everybody? Are we good?
Good.
Okay. All right. So you know, the key is that you have in-memory state for active entities, and that's the lever that we have exploited. And we can scale across commodity servers on commodity networks. And we found that almost all of our 400 customers refuse to go to technologies like RDMA, even though this is a natural fit for RDMA, remote direct memory access, right, InfiniBand. But in fact, most commercial customers will stick with, you know, gigabit Ethernet and commodity servers. So this technology is a really good fit for that, cost-wise and performance-wise. It works well. And because you have this data partitioned, as I mentioned earlier, you now have the ability to leverage all the cores to analyze the data and get real-time results. So let's go on. And I want to talk a little bit, I'm going to pass this and talk to you about Hadoop MapReduce. And I am falling behind here, so I'll go a little faster. This is what an in-memory data grid looks like. Have all of you seen in-memory data grids in the past? Understand the concept of CRUD? No, okay, I'll do it real quick. So the idea here is that you're storing business logic state. People confuse in-memory data grids with a store, with a persistent store, like MongoDB, a scalable NoSQL persistent store. But in fact, the sweet spot for this technology is ephemeral state that's associated with application logic. And as a result, it uses an object-oriented storage model, and the storage model is key value pairs where objects are instances of a class in one namespace, and you have multiple namespaces, and then you can access them by their key or by querying on their properties. So if it's a Java object, you can look at Java properties. I have an example in a minute, and query. And by doing this, you have a very nice model that maps into Java or any other object-oriented language seamlessly, and it allows you to access individual objects. And that's, again, another lever that you don't find with RDDs in Spark, for example. Now, most of the hard work is in what I call the plumbing of an in-memory data grid, because it's distributing and load balancing these objects across a cluster of commodity servers, and it's providing built-in high availability by data replication, creating 1, 2, or some fixed number of copies, not n copies, that wouldn't scale, but creating a fixed number of copies so that it's a highly available system if you lose a server. And I would say, you know, 90% of the effort in development, testing, and support has to do with availability issues. So we spend a lot of time in that area. You have a question?
If the objects are updatable, the problem is here, so what model of consistency do you offer?
Oh, that's a great question. A sequential consistency model, and implementing that, so everybody knows what a sequential consistency model is, because that fits the requirements for multi-threaded programming.
Yeah.
And it's one important characteristic, which I don't talk about tonight, is that we embody client-side caching. So when an application is doing create, read, update, delete, it has a client-side cache. You heard about that in the trivia question, and everybody seemed to know the answer. That was amazing. But our client-side cache matches a sequential consistency model so that it can be transparent to the application. The application doesn't have to be aware of its existence. It just speeds things up. Most of the other vendors do not support that model. It's eventually consistent, or they make that an option you can turn on. I don't think it's generally appreciated, the importance of a sequential consistency model.
If you can, we are short time later, elaborate on the trade-off on the performance versus replication.
Okay, I'm not sure I understand that question, but
Well, there is a cost, right? And
the
if you
cost for-
replicate more to ensure that consistency in operation. So what the function looks like. would be-
actually it doesn't hurt performance at all, except in the clients I cache, but we don't have time. Okay? So it's on our website. Go ahead.
Like, I'm trying to visualize the, like you say, patient history in the hospital. So you have the heartbeat. So you store it in memory, there's an object, the history of the heartbeat of the patient, is all be stated by the patient.
Well, there's no right way.
Is
So
the object?
the objects could be patients, and what you would store is a collection of events from for that patient, about that patient. So, if one machine is giving you heart rate, then you would have a collection of heart rate events. So you can look at the pattern of, this guy was explaining to me today how you could see, you give a medicine, and you want to see a certain change in heart rate and temperature over a certain number of hours. And if you don't see the pattern you're looking for, then you want to alert the doctor to change the medicine. So that's an example. So therefore, you would collect all that data with an object that represents the patient. And that way you have a holistic view of everything you care about for that patient. I gotta move on or I will not get through this. Go ahead.
Is that client-side caching the in-chip technology that we are looking at in place of the memory?
No. Client-side caching is purely a software concept in the application. So what an application uses is create, read, update, delete. They're calling a library. It's
Are
just,
you guys looking at in-chip technology as well in comparison?
no, we're not for this, but I'd like to learn more. Thank you.
Sorry, just one more question.
Okay.
So are all the objects represented in the in-memory cache that are available, within the totality of the database that you're looking at? So in other words, is there a prioritization based on data volatility to basically subselect or prioritize which ones go into in-memory?
Oh, well, that's, the word cache is a misnomer. People call these distributed caches. It's a misnomer because caches, harken from hardware caches where if the cache disappears or, you flush stuff in the cache, nothing changes. But typically the problems you solve with an in-memory data grid, that's the reason we changed the name to grid. They represent a complete working set that you must keep in memory. Like, for example, you can't track events for that patient we're talking about if you don't have the object in memory. So we don't talk about prioritizing that. We actually do have mechanisms for doing that and for evicting objects from the grid. But I always tell customers don't do that because you'll get unexpected behavior.
So if you have 100,000 data instances, let's say customers or whatever, then you have to have 100,000 objects
Yeah.
at least.
So
within.
You wouldn't have to, but that would be one way to design it.
Right.
And I'm just saying that design model seems to be very effective. So really the problem changes from how do you evict data to how do you provision. You have to figure out what is your peak workload in terms of memory and provision enough servers. We spend a lot of time with customers on talking about provisioning because people have that cache model, that ephemeral cache model isn't quite right. Let's just go on. So, boy, now we're getting seriously behind. Eric said I could talk for 75 minutes, but I'm not going to, don't worry. But I want to hit some of the highlights here. So these are some of the things you can do with in-memory data grids. The thing that's important is that they're very rich objects. They have lots of semantics. And when you go to implement MapReduce, that turns out to be a liability and not a benefit. So I just want you to understand, though, that over the last decade, we've evolved these semantics based on customer requests. So just to give you an example, dependency relationships, that came from a car company that said we have hierarchies of objects representing model configurations for cars. And when we decide we don't care about last year's model, we want to flush all those objects at once. Just an example of how these things percolate from customer requests. Let's go to the next slide. So the technique that we employ for data parallel computing, and you guys answered the trivia, I don't understand how anybody knew that it was 2 PMIs to do a MapReduce unless you already read something. You did that? I don't know how you knew that. I'm going to tell you that in a minute, but I don't think anybody knew that. We just use this term, parallel method invocation. I came up with that term because, when I was at Intel again, we were doing data parallel computing, but there was no notion of object-oriented data parallel computing. However, it was very well understood that you would run a method on a big data set, and then you would globally aggregate the results. And the MPI message pattern library supports that. People were simply doing it at a lower level than object-oriented. And so it became very natural to just create an object-oriented view of the standard programming model. And this is before, you know, I had not read about MapReduce. I always thought MapReduce was this model. I was quite surprised to find that it was really two faces with a shuffle step, which is a very useful thing. But this, in some ways, is a more elementary model, but in some ways, it's more powerful because it does global combining. And that's something, global aggregation is something that was always important, you know, on those multi-computers I was talking about. And it's something that is provided here. It's something you don't have with Hadoop MapReduce. Interestingly, the reducers do not globally combine the results. They just leave the results in parallel in HDFS. And so there are cases for real time, especially if you're collecting alerts. You do a parallel computation, you want to collect the alerts. It's very useful to have logarithmic time combining, which is something that was very customary with the HPC community. Let's go to the next slide. So let's talk about Spark for a minute. That's another data parallel model. And I've already told you what are the two key differences, right? So this on the surface is very similar, except the two key differences are, first of all, that it doesn't use the same availability model. And I believe the reason for that is it came out of the analytics community, not the production in-memory computing community as the technologies that I've worked on. So the notion of doing, although they address this in their original Usenix paper, they said we're not going to do data replication, we're going to use lineage. And presumably it's because it's more efficient and you get results faster. You don't have to do updates across the network. So it is faster. But the problem is if you're doing an airline reservation system, you can't afford to have an unbounded amount of time, or even if it's bounded a long amount of time, to reconstruct your in-memory data set if there's a server failure. And that's why it's very valuable to have data replication. And so the second reason is the one I've been talking about. The theme of tonight's talk is really the creation of an in-memory model of a live workload, of a real-world system. And by having the ability to use operators directly on data that would be within an RDD, if you can view the RDD as a collection of objects the way we do, then it would allow you to model a real-world system and annotate, you know, as events come in, apply them to objects within the RDD. But the Spark model is really, you know, a set of objects, data parallel operator, create new set, and everything is a data parallel operator, which is a very powerful model. But I find that these two areas are where I think the in-memory data grid can address the needs of operational intelligence a little bit better. Let's go to the next one. So this is an example, and I'll go through the implementation of this example. How are we doing, okay? All right. What time is it?
You're okay.
All right. Let's check that. Okay. Then I need a double watch. One thing it doesn't do for me is keep time. But, get the notifications. So, anyway, so
Look at it.
yes, you have to look at it. So the objects in the case of this hedge fund are portfolios. So what is their challenge? Their challenge is they have portfolios in different market sectors. Turns out they handle like thousands of these different sectors, and they organize equities, long and short positions that they hedge, right? And they were storing all this in a database. And so as the market feed would come in, every 15 minutes they would figure out whether they should place a trade. And they said to us, we need to do that faster. So our idea is let's just put this data in memory, organize the portfolios. The objects are portfolios in this case. Within an object, you have the long positions and the short positions and a set of rules for that strategy. And then the second challenge is how do you do a data parallel computation and apply a market feed to it? And so the idea we came up with is just snapshot the market feed, all the changes every second, and do a data parallel computation every second on all of the portfolios. That requires multicasting parameters. So the market feed has to be multicast to all of the objects and then apply to update their positions, then evaluate the rules and make a decision whether there's an alert, and then merge to collect all the alerts and send it to a console. That's where you need global combining. So we had to do two extensions to our MapReduce implementation to support that. Although originally we just did it with PMI, but when we wanted to compare it to MapReduce, we extended the mappers to accept parameters. And then we created a special case where if the combiner and the reducer are the same binary combiner, and there's only one reducer, then just go ahead and use our global combining and don't bother with the reduction step. That's actually built into our implementation. The net result is you can do this very efficiently. In fact, you can do it in about 300 milliseconds. Have a little video of that in a minute. Let's go on to the next slide. So I want to walk you through how this is done. The first step in this object-oriented parallel method invocation is parallel query. And that way you can refine the set of objects you care about so that you don't have to operate on all of them. So go to the next slide. That's property-based queries. And here's a little bit of code. Hope people like Java code. Have C# too if you prefer. Okay. So this is a portfolio class. You can see what I'm talking about. That's the object you'd store. You'd have a namespace in the grid that has objects of that class. Notice they're collections of long and short positions and other properties. And you can attribute those properties so that you can do a parallel query shown at the bottom. Now this is the real deficiency about parallel query. I would say that 8 out of 10 customers that we talk to, this is not a vendor pitch, but I'm telling you all my customer experience. I hope you find that interesting. They say, oh, I want to do parallel query. So no, you really want to do parallel method invocation. They say, no, I want to do parallel query. So the problem with parallel query, just look at what happens here. You're going to go do all this data parallel work to send all the results back to the client. So all the queried objects go to the client. Now what do? Wouldn't it be better, instead of writing a for loop in the client to analyze it, push the method out to the grid and just do everything in parallel out in the grid and just collect the final result? And so that's the beauty of parallel method invocation. Let's go to the next one. So to do that, you create a method which evaluates, which takes a market feed snapshot, it takes a portfolio, and you embody in there the code to update the positions and evaluate the rules and decide whether to create an alert. And if so, you create an alert. And then you just have another method which merges all that, combines it, a combiner. So the eval method, we call it, is very much like a mapper, except it has an input parameter. The merge method is exactly like a combiner. And notice that it would, because we're going to do global combining, it's equivalent to having one reducer that acts as a combiner. Go ahead to the next one. So this is what it looks like. It's pretty simple. There are 2 slides here. One slide shows you how you construct the eval and the merge methods. Notice that this is actually the method on the class, on the portfolio class, but we just wrap all this in an interface. So you create an interface for eval and for merge. And notice that the methods also use hydrated data. They don't have to use CRUD to get data out of the grid. The data is hydrated for them and made available to these methods. And go to the next slide. And so to do a data parallel computation, you just simply, on the namespace of objects, you just say invoke, supply some parameters with the class types, the parallel query, and then you get the result back, which you can then deliver. So that's a little bit more work than a parallel query, but the power of it is much higher because all of the analysis is done in the grid. The point of showing you this slide is you see how little code is required to do data parallel computation. It's much simpler than people think, and much simpler than MapReduce.
So you execute next to the data, physically close to the data.
Yes, in fact,
You are moving methods, not moving the data.
that's right. So what happens is we move it. First of all, we built an infrastructure. You can have a set of slides, by the way. I'll be happy to send them to you unless you want to. So we built a thing we call an invocation grid. So you can pre-spin up a set of JVMs on all the servers that make up the grid, and then you can ship the code out to them. So you just specify the jars you want to ship out, we just ship it out. And then when you invoke the parallel method invocation, all the code is there, the methods you're going to run. And it's only the invocation itself, a little message that says run this piece of code, and also the parameters. And we use software multicast to get that out as efficiently as possible. Then on each grid server, we run the parallel query to select objects on that server that are relevant based on the query. And then we simply execute all of the eval methods, and then we do all the merging. So you end up with one object on that server. Go to the next slide. So once you've merged all the data, then you just simply do this global login merging to get a final result, and that's what's shipped back. So go back 2 slides. And you can see that's where you get the final result up there. Sorry, not there, right here. To invoke result. And then inside of that is the actual data. So that's where the result comes back, and all of that multicast out, parallel analysis and combining just happens under the floor when you say invoke. All right, go forward. One more. Okay, so just to show how this scales, we ran this on that backtesting problem, I don't have it for the hedge fund problem, but for backtesting, we ran on 75 servers of Amazon Web Services just to show, okay, we can handle terabytes of data. And this is churning data. So this data is churning at the rate of 1.1 gigabytes per second, and you can see you still get nearly linear scalability. If we had time, I'd ask people, why do you think it's sublinear here? Slightly sublinear, but we don't have time. It's the noisy neighbor effect.
Good with it.
Okay, noisy neighbor effect is what we think. We didn't have time to look at it closely, but we were running on virtual servers with who knew what kind of performance we're actually getting, or whether we were on a different chassis, you know, for some of the servers. When you get up into 75 servers, weird things happen. But in any case, the point is that even at this update rate, you're getting a nice linear speed up, and you're handling the entire analysis in 4 seconds. That's a terabyte of data. It's like a whole disk full of data being analyzed in 4 seconds. So it scales well. I'm very confident this will scale to handle most of these operational intelligence problems I've discussed tonight. Now, we were talking about the cache consistency model, and that's what causes the drop in throughput. It's because of the fact we're maintaining sequential consistency that the updates have the effect of flushing client-side caches, and that's why it drops when you go from no updates to 1.1 gigabytes per second. Go ahead. All right, so this section, there's 2 sections left. There's a little discussion of Hadoop MapReduce, which I'll do quickly, and then there's finally a video of that hedge fund demo, and then we're done. So, do people want to hear about how we implement MapReduce with this? Okay. All right. We're still good. Not dinner time. Okay. All right. So, you know, our thought was about 2 years ago that if you could do MapReduce, people know how to do that already. And as I said, I think the design pattern is with us for the ages. It's a very powerful and useful design pattern, but the problem is it lives in a batch processing world. So let's bring it to an in-memory world so that you can work on live data, leverage your skill sets, but work on live data and get much lower latency response. That's very cool. I mean, to be able to write a pure MapReduce program and run it without having to go to HDFS or without having to go through the batch scheduler. And then with some of the extensions I talked about earlier that we made to make it a little bit easier. Go to the next slide. So I was explaining before, when you run a job, you know, we bring up this invocation grid of JVMs, and then we run the MapReduce program in the grid and send the results back, and we can persist the grid. So that way the latency goes even lower. Go ahead. Now, this will fit in. I'm going to come back to the question about, you know, that answer was actually wrong about which version of Hadoop do you need. But I didn't want to contradict anything. But I'm going to tell you that there's a slight detail in there, which I'll tell you in a minute. But we are designed to work in a variety of environments. So first of all, it's correct to say we have our own MapReduce execution engine. But for the purposes of unchanged MapReduce, to run a MapReduce program without changing a line of code, then we actually leverage the client-side Hadoop library. So to run in the Hortonworks environment, we actually, on our website, have the Hortonworks client libraries, and we ask you to drop them into a folder, or directory, sorry. And then you actually, when you say map, you're calling the Hortonworks mapper class, and that calls, but job control is captured by us, so it never goes through your execution pipeline. It's simply the client-side, you know, semantics and class definitions. So that's the one constraint. So we actually have for every different distribution, Cloudera and Hortonworks and Apache and IBM, we have client libraries which you link to. But it's the same in-memory execution engine in all cases. Now with Yarn, you don't have to change any code at all, it just works. In fact, Hive will run on top of the in-memory data grid because of the fact that Yarn is allowing it to run without any code changes. And we've demonstrated running Hive on data hosted in the grid. So if you look at this overall architecture, you have your data warehouse here, and you can some jobs can go to the data warehouse with Spark or MapReduce, and other jobs can be directed to the in-memory data grid, which is capturing live data. So you see how the operational intelligence and the business intelligence can be implemented in a complementary way in one platform, although we can run without any installation of that platform at all. Go ahead. So as was correctly answered with the trivia question, we run in 2 phases. We run the mappers, and notice because it's code compatible MapReduce, you can use any input format, so you can get data from HDFS or from the grid itself. And then After the mappers run, we use aggressive combining to shuffle data and push it into the grid. And then we extract that data and feed it back to the same set of JVMs to run the reducers, and then you can output to wherever you want. So that's the way this was implemented. Go ahead. And I'm going to skip some of the details, but let me just explain it. We have an input format for the grid and an output format for the grid. So from the point of view of a MapReduce program, it's just another data store. It's nothing special, but the data can be live and churning. And that's the power of this. It can't be as big, you can't store petabytes of data, but you can store live data and do MapReduce with standard MapReduce programs. Go ahead. And also, we provide this thing where we can wrap your favorite input format so that we can act as an HDFS cache and store as the key value pairs flow into the grid, flow into our MapReduce engine, we store them in the grid and can serve them up in a subsequent run. We thought people would find this very useful. And it's very transparent. The problem, the limitation is it can only hold as much as you allocated memory for. Anyway, go ahead. Now, the thing that we observed when we first implemented this, which was a big surprise, remember I told you the objects that have rich semantics, car company, dependency model, and all that? Well, that object model doesn't really fit MapReduce at all, right? Because MapReduce, like if you do word count, has hundreds of thousands, billions of key value pairs, which are really tiny objects, 100 bytes maybe, as opposed to multi-kilobyte objects that we normally use. So we implemented a completely new storage model for small key value pairs. Go to the next slide. And that storage model chunks them up and serves them in a pipeline way to the mappers and it pipelines them back out of the reducers. So there's a lot of optimization that has to go on to make MapReduce work well with an in-memory storage model. But one of the values you get out of that is automatic tuning. So the in-memory data grid can automatically determine the number of splits and automatically determine the number of partitions. So it's virtually self-tuning. You don't have to worry about tuning this to run effectively. Go ahead. And I'm going to skip this. These are some of the optimizations we did. Skip that. And we're going to skip the high ones. I talked about high. Keep going, keep going, keep going. All right, stop here. So now I'll wrap up with the financial services example. We just looked at that. Go to the next slide. So this is the proof of concept UI that we built. And so what's going on here is that every second we're going to send out a market snapshot, market price snapshot to all of the servers and apply it to all of the strategies. There are a couple thousand strategies in this proof of concept. You're going to see a video in the next slide. And then we collect the alerts and we mark the strategies which are alerted yellow. Hopefully you can see that. And then when you click on a strategy, it opens up that object. This is where CRUD is valuable, right? You just go in and look at that object and see the data in it. So you can see all the positions, the allocations, and you can see why it was alerted. There's a yellow line there that shows why that particular portfolio was alerted. So let's go to the next slide and click that. Hopefully that will work. There's no audio. It was designed for me to talk over it. So first we're just showing, this is just a video. This is on YouTube of this UI. And you see the strategies are on the left. And this is to give me a chance to tell you what's going on. And you can see some are highlighted. And then it's going to show you the various fields here. So you see the ticker symbols, long and short. And you can see in real time that the prices are changing, if you watch that. And you can see the exposure is changing. And it goes more to the right. And you can see interesting stuff. And the actual allocation, the deviation. When the deviation crosses the threshold, we alerted that portfolio. So this is running on the grid. That's taking 300 milliseconds or so, plus or minus a few, and to run. And we're only starting it once a second, but it runs very, very quickly. And that's Apache MapReduce running. It's the same code. So we converted that to a pure MapReduce code, adding those extensions, and compared it to Apache. You can see that takes about 15 to 20 seconds. So that's the difference between batch processing and in-memory. And it didn't break, the video ended. Go ahead. See if you can get out of there. X that. And, or X there, sorry. And just hit Shift F5. And that'll take you back to the top. Shift F5. Yeah, go to the next slide. And so let's skip these and I'll just do a recap. Okay. So what have we learned tonight, or what have we talked about is operational intelligence is really valuable for live systems because we can provide real-time feedback and enhance the value of those systems. And we see a strong interest in e-commerce and Internet of Things in many verticals. And data parallel computation run on an in-memory data grid provides a very simple and yet fast platform to implement that. And the reason is because of the fact that it's designed for production environment with high availability. It's a very simple data parallel execution model, and it allows you to get very fast feedback with latencies under a second. And so that's it, and thank you very much for hanging with me.
Before everybody gets up, we are going to have a QA, and I want to give a great big round of applause to Dr. Bill Bain. I saw a number of people have phones up, and one guy with a tablet taking pictures. Please go to our meetup page, nycsequel.com, and post them up. Everybody should have access to post up photos on there. And let's take the first question. Yes. Sorry. Yeah.
So about partitioning, how do you partition the object?
And
you take it to a hand and I say the object down to the
Yeah, there are many techniques people use for partitioning. Going back to Memcache days where you have to partition yourself. We have our own proprietary model for partitioning, but we group objects in such a way that we can have client-side tables that can, if you know the key to an object, you can immediately go to the server where that object is hosted. I will say we use techniques that derive from distributed shared memory. So they use a level of indirection, and by using a level of indirection, you can add servers and lose servers and reload balance without having to reconstruct the client-side view by the developer. But the system itself can keep track of where the objects are because of the fact that you use a level of indirection. But if you just go to the distributed shared memory papers, we just use that technique and applied it in an object framework. The actual code we have.
Next question.
Yeah. Yes.
If you cannot break up the application's object graph in such a way that each node has, self-contained, independent set of objects to work on, then how do you deal with identity of the object? Is it a copy on every node, or is it?
Oh, no. An object exists only on one node with a replica on another node. The replica is an abstraction. It doesn't come into play except when the object is updated. In other words, when you're writing a data parallel computation, you're not aware of replicas. It's a level of abstraction down. But in terms of your question, I think was, if you don't have enough objects to partition them evenly, our partitioning scheme is just statistical. So if you have a collection of objects, say 1,000 objects and 10 nodes, it's just going to partition statistically based on hashing the key. Some number of objects to each node. It doesn't actually do it that way, but it's logically a hashing algorithm, statistical mapping, so that you will always have some percentage on every server. Well, the problem we don't solve, maybe what you're getting at, the problem we don't solve is one that Hadoop does solve, which is that if you finish early on one server, we don't shift work from another server. Because this is more fine-grained, it's just faster to let some servers finish a little bit early and start their combining and let the others catch up.
So maybe I'll rephrase. So my question is, when you send this,
we're really short on time. Dr. Bill Bain will be here for one-on-one afterwards, so you're not.
We can
losing
talk
any
more.
question.
I'd like to hear
I just got to get more people in. Yes.
What are the best and the worst use cases for that? Like when we use and when we do not use?
When you are modeling a system as a set of objects, I mean, it's pretty much what I said.
Yeah, but use cases, like
Well,
real
so
world.
like e-commerce personalization engine is a very good use case. I talked about several examples.
Yeah.
But it comes down to live systems where you have entities, and you say, these are stateful entities that I need to represent, and I need to look at them all in parallel. They're independent entities. So here's an example.
So not sequential, but mostly.
Yeah, they're embarrassingly parallel. So
Okay.
like a clustering algorithm would not be a good use case because you have to do a lot of correlation across different objects, a lot of communication. Anytime you have to communicate, I'll give you another example, a distributed simulation, the example I looked at where you have to keep a simulation model of time that's coherent across all the servers. That requires a lot of communication, and it turns out that's very inefficient to do. If you're modeling, say, air traffic, there are cases where there's a lot of, or weather simulation has a lot of nearest neighbor communication. That communication can kill you. So These are all embarrassingly parallel problems. Look.
That's all the time we have tonight, but Dr. Bill Bain will be here for one-on-one questions. Feel free to come up right now and ask him. Thank you all for coming. Thank you, Dr. Bill.